3, 2, 1. Oh, hello everyone. August 20th. So after 2 days of bombardment, finally, I got a little bit break. So we can do this fast. So alright, so we do this fast. We have 3 problems, right? Saved. I'm gonna try this one first. Basically resolve this. I might as well just cancel this and put it in Python. Right? We'll resolve this using Python. Just see if I still remember how this one is done. I still do. And after that, probably tomorrow, yeah, we're gonna resolve this. You know what? We're going to set this to Java, right? We're gonna do this in Java. Oh, do this in Java. My. That's okay. We can do that. We can do that. All right, let's solve this one first. Repeated substring pattern. Given an S, check if it can be constructed by taking a substring off it and appending multiple copies of the substrings together. So if AB we say true, ABA we say false, ABC. So how would you do it? We just go through and that's a good question. How do you know that you're repeating yourself? If it can be constructed. That's a good question. I mean, you start. When you start, you check and you put it in and you put it in. And when do you know it starts to repeat? What if something has occurred before? But you can never be sure, right? What if I do AB, and at the end I change? This is actually a good test case. Now this is not like this. Right? If you have this, you have to check all the way to the end to know that the second one is bad. I'll just return false. Huh. Yeah. This one should be false. What would be a faster way to check this? I mean, you pick A, and then you see the next one is A, is not. Then you pick B, then you see if it's AB. Then you have to see if the next one's AB, if the next one is AB, if the next one's AB. Well. There are some easy checks initially. We can counter the whole thing, right? So each, I was going to say each one is the same. That's actually not true because I have like AAB. Then A is like double the amount of B. So that's not it. A pattern. Huh. I'm thinking like you have to go through all of them, right, to find a pattern. But that will be O(n) squared, right? You start with 1, and then doesn't work. And then start from 2, doesn't work. Start from 3, 4, 5. You just have to go through every single Is there a better way to handle this? Is there a better way? Well, if there is a pattern, then each letter's indices shall be periodic, right? It shall be periodic. Like, what do you mean by periodic? Like 0, 0, 3, 6, something like that, or something something. Then you're just replacing this problem with another problem to find if there's any pattern in the numbers. But is a pattern with numbers is easier problem to solve? What if the pattern is very complex, like A, B, C, D, D, E, F, like that? It's a very complex pattern. Or like it's actually like multiple, like A, B, A, B, A, like that's a pattern, right? Do you have to really get that in order to find the same pattern? I wonder, there gotta be a easier way to handle this, because it's an easy problem. But in addition, like except from like brute force, I really don't know. I mean, this is easy to detect, a false. Okay, a false case is easy to detect. Okay, so that's a trivial case. We're done. Now the case, actually it's not even a trivial case. No, it's not. It's not a trivial case. I mean, each one, you can count how many, right? And yeah, I don't see it straightforward. I don't see it straightforward. What else? What the hell else can we do about this? Can we like say front and back? Like 2 pointers, one on the front, one on the back? How are you gonna handle that? Well, I have a starting position, right? It has to start with something. So at the end, we can try to find a or like we say, we have something end at end position. I mean, that's the same thing, but I think it will be easier to say this. And here I have an end position. So in the start, we can just search for the first that has this end position. So we can say, okay, so that probably is the same. Then we can check if these two are the same. Okay, if they're the same, then we solve the remaining. And that will be, then we know what it is. Then we can just go through to see if it works. So yeah, here's the proposal is we have whatever things, right? And we find this, okay? And then we need to be here. We start to go one by one, because that's the end. So if we have the same thing repeating, then we'll find, let's say, the first one, they're the same. Then we check if this is equal to this. If it's not equal, then we keep searching, right? We keep searching. This, let's say these are the same. Then we say, is this equal to this, right? Yeah, we have this. We just search. Is this equal, not equal? And then we can go all the way down. And if we pass the halfway point, that means it's not possible. For example, I have this ABC, 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 A. I just do this, right? So the last one is A. So we check this. These are the same, right? Then we say, okay, it's possible. Maybe everybody is made from A. Then we need to check if there's only A in this. Yeah, we check, right? We check if it's just A in this. and we say, oopsie doodie, no, it's not. Right? It's not. Then we say, okay, that's not working. Nah, just keep searching. Boom, this A. Then we say, is this equal to this count in 4? Okay, these are equal. Then we check the one in the middle. And then we see, oopsie doozy, size is smaller. Then no good. So we keep searching. The next one will be this one. So I say this, it's more than half. So this one's not possible. So what's the total runtime of this? Well, we have to go one by one. That's already O(n), right? And along the way, if it's possible, right, then we will search. So we from the front, and then we'll search the remaining. And if it's possible, then we're done. If it's not possible, then we will search this. Hopefully, it will be wrong very fast. I'm gonna give this a shot. Okay, I'm gonna give this idea a shot. Is this gonna be working? I have no clue. It's surprisingly not that easy as I had expected. Surprising. I thought this is a walk in the park. Okay, I was not thinking right. I don't know. But anyway, we are going to say the end. We're going to say end. No, it's going to be char, right? Char. The end shall equal to s dot char at s dot length minus 1. Right? I'm going to say for I equal to 0, I smaller than s dot length. Actually, yeah, I just do that. It's okay. I plus plus. Okay. Then we say if s dot char at I is equal to, and when you substring, okay, when the Java substring. Java just calls substring. str.substring. Begin index. Begin and end index. Okay, so if they're the same, and s.substring, begin is 0, end index is gonna be I. Oh, I mean, not really I, but it's equal to n, so it's fine. If this is also equal to substring s dot length minus with the start I. So I say I is 2, 0, 1, 2. Okay, so that shall be minus 1, minus 2, minus 3. So minus I minus 1. And we might do this plus 1. So this is 0 to I. So it's I plus 1 size. And this to the end, I plus 1. So if these two are also the same. Oh, string value has to be compared using equals. Oh, I didn't know that. Compare strings. Reference equality. Test value equality. Objects are equal. Oh my god. My god. Dot equals. Good catch. IDE. So if this is equal to this, right, and then if the substring is equal, then we can check with inside. Now we can say, I like to do the substring calling once. Okay, I want to do substring, so we say string candidate shall equal to this. Okay, that's all I want to do. That's the substring. Then what? Okay, then we say if candidate dot equal to the end, then we can do in the middle to see if it works, right? Then what do we say? We say for int j equal to I plus 1, j start from here, j plus candidate.length right? J plus, let's say, length is 3. Plus is minus 1. So smaller than s dot length. J plus equal to candidate dot length. Right, so j start from here, and j plus this has to be smaller than that. And every time we're done, j will plus the co-candidate length to the next one. So we're trying to say if everything within this is equal to the target, right? Then we simply goes if candidate dot equals s dot substring j start from j end index, or is end index inclusive or not? It doesn't, it's not inclusive, so it has just to be j plus candidate length. Right, if it's not equal to, then we'll break. Candidate, right, if this, we get a candidate. Right, if it's just equal, then we will go. Then we can say a Boolean value found can equal to true, and then found equal to false. It's like a flag. So we get out, we say if found, then we'll return true. Okay, otherwise keep going. And we say if the candidate length, say if cand dot length is larger than times 2, it's larger than s dot length, then we'll break. Right? Then at the end we'll return false. Well, this feels hard. I feel like, well, someone's going to say hard coded, but that's just brute force. Break. Okay, these work. through all of these. Maybe it works. How about this? This is a very edge case. 1. False. Okay, we'll give it a shot. Oh, I've done this before. We passed, but this feels, oh, it's pretty good performance. But really, that's the best way we can think of to do this. So what's the runtime? I mean, we can say will definitely not work. Like ON. I mean, we check one by one. That's ON. Once we're done, that's still ON. If it's good, then we check one by one. And the worst case, I think, is all A's, and then in the middle we have a B. So every time we check, we have to go through the entire thing. I intend to call this O(n) squared. Yeah, not very happy with this solution, with this brute force solution. Basically, we check S one by one from the front to find a letter that is equal to the end of S, and use that as a candidate to see if the entire string can be subdivided, can be formed, right, by that candidate. I feel O(n) squared, but for whatever reason, just give us this result. You just see the solution. It's kind of weird. Okay, what are the... That must be the right solution. What's this one? Potential. I don't know what I was doing there. What's this one? Oh. Oh my god. S plus S. What's this 1 to minus 1? We get S. We get another S. But you should put them together. And then 1 to minus 1. So only take the things in the middle. Okay, so here's what it's trying to say. We get a string ABC, ABC, we add ABC, and then we kill this and see if ABC and ABC is in between this. Because if I have k repeats, right? I have k repeats. I have k repeats here. So in total, we have 2k repeats. If I remove the front and back, then I have 2k minus 2 repeats. If initially I have k repeats, k has to be larger or equal to 2, right? Therefore, 2k minus 2 will be larger or equal to 2, right? No, 2k minus 2 will be larger or equal to 2, larger or equal to k. Yeah, because k larger, so 2k larger or equal to 4 minus 2. No. A string has k repeats, right? It has k repeats. So if k is larger than 2, then k plus k or larger than 2 plus k, which means 2k minus 2 is larger equal to k, which means we'll have at least k repeats, and it means we have at least one copy of this. Now I see. KMP. What the hell, KMP? I'm not doing KMP today. I do not have mental capacity for KMP today. What the hell? Nah, no KMT today. I don't feel like it. Alright, what's this? Using divisors. Oh, I see. I see what you're doing there. Okay, that's, yeah. String concatenation. I mean, I guess we can say finding S in T takes O(n) squared in Java and Python, but O(n) in C++. Oh, you do this first, and then you use KMP to find a substring. Yeah, if you use this, it will be asked, can you implement KMP? And I'll say no. Well, you give me Google, I'll implement KMP for you. But If you wanted me to do it from memory, no, I can't. I tried many times. I cannot. I mean, but yeah, this is the right way. This is brute force. I mean, this is the same, right? This brute force, the brute force I was thinking about, isn't that exactly the same as this? I mean, we're not dealing with every single possibilities. We're choosing the ones that really works. So we're not dealing with every single possibilities. So do a little bit smarter, but the overall is the same. But let's do this, right? Let's do this. So it's kind of solution 2. All right. So the correct, I shouldn't say the ideal, right, solution is to repeat s. Remove its front and end, right? Removes front and end character, and see if s is still a substring of the remainder string. So proof, right? If s contains k repeats of a substring, right? Then duplicating s produces 2k such substrings. Removal of the front, the first and the last character at most removes 2 substrings, which means the least number of substrings in the remainder string is 2k minus 2. Now, since we propose that s is a repeat of the substring, it must be that k is larger or equal to 2. Right? If k is equal to 1, then there's no repeat, right? Thus, k plus k must larger or equal to 2 plus k. Thus, 2k minus 2 larger or equal to k. In other words, let's do this one here. In other words, the remainder string must contain at least k repeats of the substring, or the string as itself. Therefore, by checking whether s is a substring of the remainder string, we can determine whether s can be expressed as k repeats of a substring. Now, the difficult part is to write an algorithm of O(n) complexity for substring match. That can be done via KMP. I think there's another one. KMP is one. It's the first one. I think if I remember correctly, there's another one, which is easier to implement than KMP. Yeah, but this can be done like KMP. But having done KMP multiple times, I am very positive that I cannot write KMP from scratch out of memory, from memory. Yeah. So we'll mention it to the interviewer, but sorry, can't implement it. I don't know, is this like too lazy? Well, I guess you can think of it the other way. If the interviewer wants you to implement KMP on the spot, I think they're pretty sadistic and probably don't want to work for them anyway. Come on, you just search online. It's a tool, right? It's a tool. So if using KMP, that's ON. Otherwise, ON squared. We'll implement this, right? We'll implement this. So by implementing this, we need to know how to do concatenation. Is it just plus? String concat. Is it just plus? Yeah, which is plus. Okay, we can plus, it's a plus operator, we can concat. That's good. So how to check substring in string? Check substring in string. It's just contains, I guess. Contains. Okay, so we're gonna say, oh, I can do one, right? I can do one liner, return s plus s, right? But that's no good. We have to substring this. Dot substring 1 to what? S dot length times 2 minus 1. Yeah. Dot contains s. There we go. This is O n squared. Should be fast. No, it's not. Wait, my method is actually fast? Oh wow, I didn't realize this one is actually pretty fast. Is it technically O n squared? But I think it's just I didn't check every single possibilities. That's why it's kind of fast, right? Because I first have a selection on candidates. Only if candidates is good, then I go through. So I guess a lot of things gets eliminated. And the first one that's true, and I return. I wonder how KMP will work on this, but I really don't want to do KMP. I really have no intention to do KMP. That's how you're supposed to use this. Okay. My God. Oh no. What the hell? Is one even run? Oh, it doesn't work. Can I don't know, Control F? Can I replace this with 4? I guess I can. All right, so KMP search, pattern, and text. That is not Java. C style, so I have to change this into this. That's okay. I don't need system out. Yeah, this is not necessary. What do we return? Void. Void? Oh, the ones that deleted, I should return true or false. Okay, so yeah, return true or false. Return true. If the whole thing, return false. Then we go boolean on this one. Return value of methods never used. That's okay. All right, we'll do public. Right, and this is probably we'll do private. And oh, I don't need this. KMP string. Oh, I should do static. Right, I should do static. Static. And then this one is not working. Non-static method cannot be referenced from a static context. I will do static too then. Static public. That's okay. Static public. That's okay. All right. So instead of we call this, we will say return. Let's call it KMP. Okay, KMP. So we have KMP dot KMP search pattern is S. And text is going to be this. All right. Let's try this and see if it's any faster. Yeah, this one just curious. I don't even want to know how the KMP works. I mean, I do know, but just don't want to go into details. Is this working? Ooh, what the hell? Oh yeah, it's working. Wow, it takes 0. Oh wow. Man, KMP might really be fast. Hold on, let's try this. I'm surprised. I mean, KMP is fast, right? It's faster than directly, but it's not as fast as my original solution. I don't know. Yeah, it doesn't matter. Doesn't matter. I can say, let's put it here. The solution below does not use KMP. If using KMP, runtime is this. Otherwise, it's 70. Yeah, and its runtime is 74 milliseconds. Right? Okay, that's it. That's all I want to do about this. Done. Not you. Okay, let's go this one. 20 minutes. Let's get this done. Critical pseudo critical edges. Okay, so we will use Kruskal algorithm. And if we go through this one more time, Kruskal algorithm says if we sort all the edges and we start throwing the smallest, okay? Smallest, the second smallest, all the edges we throw together into a graph. We want to build a minimum spanning tree. So we keep throwing. Any edge that will create in the cycle should not be added, they should be removed. And if we can throw n-1 edges, because the minimum spanning tree for a tree of n nodes, the minimum spanning tree must contain n-1 edges. So if we can throw n-1 edges into it, that is a minimum spanning tree. And it's also because every time we throw an edge, it's the minimum, so it will become a minimum spanning tree. So we'll first do an MST to find the value, the weight, the minimum weights. Okay, so that's the standard. And then we'll go through each edge to eliminate this edge. Okay, each one will say this edge does not include. So we'll eliminate this edge, and then we run MST again to see what's the minimum weight. And if the minimum weight is larger than the standard minimum weight, that means the edge thrown away is critical, right? You cannot do without it. So you include that into a critical. So it goes through all that, and we get all the critical edges. Next, what we want to do is we say a certain edge must be part of this. Okay, we say this edge must be part of it. So we include this edge, and then we run MST. If the result is equal to the standard, that means that edge must be a pseudo-critical. Okay, so that's the basic idea, and we are going to do this. We say this is 2.7. That's actually not. I think that's one of the, which day was this? I don't remember, doesn't matter. Let's do 1489. It's okay. Treat this as just, not Java, come on. Treat it as a regular problem. Okay, so a couple of things. We need a union find, because we need to use union find for, we need a union find for decide whether an edge will cause a cycle. But it's like if the two nodes in the newly added edge is already in the graph, then if you add that, that will cause a cycle. So we have a parent, like usual, the list. And here, this because I've done it already, I know I should not do a rank, I shall do a count. All right, count, let's just remind ourselves of what count is. Self dot count I counts the number of nodes in the graph rooted at I. So we need to use this to decide whether after we add n-1 edges, whether it's connected. Right? It could be it's not connected. All right, so find is, that's straightforward. That is straightforward. We're gonna return an integer. This one not return anything. Okay. If self.parent x is not equal to x, self.parent x equal to self.find, self.parent x, return self.parent x. Yeah, union find I use so many times so I can write it, and it's honestly not that hard to write, but KMP, my god. KMP is a completely different beast. Like, really different beast. Okay, if px equal to py means they're already in it, so we return false. That's important. Else, then we say if self dot self dot count px. If it's larger equal to self dot count py, then everybody need to go to px. All right. Then we say self dot parent py shall equal to px, and self dot count px plus equal to self dot count py. Everything that's rooted in py should we go to px. Right? Else px shall equal to py, and self dot count py plus equal to self dot count px. Okay, so that's our DSU. We need to write another thing called MST, right? MST. There are a couple of things we need to pass to the MST. So we can just def MST. We can actually say find MST weight, right? This is what we want. So we need, what do we need? We need a edges, right? We need edges, but we already have edges, so we don't really need edges. We need things that we need initial weight, initial edges, right? Initial weight, initial edges, and band edges. Yeah, we use a set. All right, band edges. I don't really need to use a set though. I think band edge, we only have one edge to band. And the edges is 0, 1, 2, something, something, right? We need to sort the edges. Oh yeah, we need to sort the edges. Oof, sorted edges. Band edges, band edge. Okay. Find weight will give me a weight. All right, let me sort the edges first. Okay, we're gonna call sorted edges equal to for AB weight in edges. We want I this in enumerate edges. Then we do ABWI. Maybe we can spread. Maybe. Actually, let me try. Can we spread? For I tuple in enumerate edges, can we spread like I? No, I'm thinking about this I. Yes, I can. I can do that. I can do that, but it's probably not the most efficient because I want to put a W first. Okay, then we're gonna sort this, sorted this. That's sorted edges. Okay, then we're gonna find MST, right? Find MST. We have an initial edges, so we're just gonna go through and we have to add the initial edges into it. So we have to have a DSU equal to DSU n, right? Initial edges, so for EI in initial edges. We can go this, we find a 1, then we say DSU dot union edges EI 0, edges EI 1, right? We union all that. Then we say for weight ABI in sorted edges. If I is not equal to band edge, then we shall say if it's not equal to band edge, yeah, I should say if DSU, if I is not in band edge, okay, and DSU dot union AB, if I can union them, right, so it's not in there already, then we'll say Oh wait. Let's call it W so we don't have to. You know what? No. Weight equals initial weight. Edges. We don't need to know the edges. I just need to know the weight. Okay? But I need to know the count. Right? How many edges have been included? Okay? How many edges have been included? So we can say edge count. Line initial edges. Right? Now we always check if edge count is equal to n-1, then we should break. So we'll do this, blah blah blah. W plus equal to W. Can't use W. Weight and edge count plus equal 1. Blah 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 blah. When we get out, then we say if edge count is equal to n-1 and DSU dot count, because we have to show everybody's in it's connected. So now count what? DSU dot find 0, doesn't matter, any node. This has to equal to n. If both, then we shall return weight. Otherwise, we shall return something to indicate that it's not possible. What do we do when we say it's not possible? We can return maximum, right? Can return maximum. It's probably not the best idea. Return the weight. Because in one of them, I say if the weight is larger, then it's critical. And the other say a weight is equal. So I just need to return a weight that if it's not possible, right, and it's not critical. So it cannot be bigger, it has to be smaller. Let's return -1. Okay, so that's to find. Then we'll call min weight, min W equal to find this. Initial weight 0, initial edges is nothing. And band the edge is -1. We don't have any band edge, so we get a minimum weight. Then we'll say for all the edges, right? So we can do, what do we do? We'll do criticals, right? Criticals equals this. Now for edges, for each edge, right? Let me say for I in range line edges. For each edge, we say current weight shall equal to find MST. Initial weight 0, initial edge is nothing, but band edge is I, right? Then we say if this is larger than min weight, then critical start append I, that's the critical edge. So done. Now we want a pseudo criticals for I in range, again, line edges. For each edge, we say if find this. Now we have initial weight. We can do edges I 0, 1, 2. Initial edge. Only have one edge. Initial edge. Only have one edge. Band edge. Initial edge. So I don't even need this. Right? This is just gonna be initial edge. So edge count is 1. We just add 1. As long as we don't include a band edge, everything is fine. So here I have this. Initial edge is I. Band edge is nobody's band. We say if this is equal to mean weight, then pseudo dot append I. Now pay attention here because we have to remove the critical, right? So if I is not in criticals, and which means this has to be a set, right? So if I is not in criticals, right, and we include initially, and if it's equal to, then it's pseudo. So we're going to return a list of criticals and pseudo criticals. All right, let's see if this one's correct. Bunch of test cases. Oh, see, the syntax starts to fight each other. Yeah, this is wrong. Ew, I have to add another check. If init edge is larger equal to 0. This is on -1, -1, -1, -1. This has actually value. Okay, try this. Something, something, not correct. It's like I had this before. I don't know. What did I do wrong? Yeah, I don't know, right? We just put in here, I think a small mistake. Maybe we have a small mistake that didn't realize earlier. It's all right. And edges. Alright, first make sure this is correct. Yup, this is incorrect. Edge count. Start with 0. If this, then edge count plus equal 1. Gotta be kidding me. Okay, let's see what happened here. Print, let's see, what weight we get? 0. That's very bad. Maybe sorted edge to make sure it's correct. Yeah, sorted edge is fine. Sorted edge is fine. And dish. Oh, I didn't return. There we go. Sorry. Yep, just forgot to return. Silly mistake. Silly mistake. We got another wrong. What the hell? It's the same problem as last time, right? Didn't I check this already? Didn't check well enough. I think this one should be right. Yes. Critical. None of the critical. Oh, yeah, I realized. Yeah, I remember. This is not, yeah, it's math.inf. There you go. Yeah, because it's not right, then the weight should be max.inf. I don't know why I thought it otherwise. It should be math.inf. All right, I try this. Sorry. Yep. Yep. I got it. This is a Python implementation. It is cleaner than the Java one because the find MST weight function input only requires one initial edge and one band edge. The Java version uses hash set for both. Because in here, I put the critical edge inside the initial edge, which don't really have to. In fact, we don't even need initial weight. Come on. This I don't even need. Right? Because initial weight is just going to be edge count, weight equal to 0, and a weight is just going to be plus equal to, that's going to be edges 1. All right? Which means I don't even need this. I don't even need this. I don't even need this. Huh? Oh, my bad. 2. There we go. Yeah, that's that. Yeah, let me do this one more time. Wait, what's the runtime for this? I don't really care the runtime. Crucial. This is alpha. That's the union find. M squared. What's M? Number of edges. We have to go every single one. Every single one. Okay, so in here, we have to go every single one. Yep, O(n) squared. O(n) squared times union find. All right, one more time. Do this one more time. Now I'm happy. Okay, this page can be turned. All right, that'll be it for today. Tomorrow we have Java for this topological sort. I'll see you guys tomorrow. Adios.